A great pleasure to have Professor Thierry Bodineau from IHES in Paris, in France. He is going to tell us about some large deviation for reaction diffusion system. Yeah, please start.
Thank you very much for the invitation. I have to say it's a great pleasure to be here. Originally, I was thinking to give a different talk, so I gave a different title. And then I realized that with discussing this week that could be possibly of interest to some of you who are working on active matter to have a review of a few things, a few lattice gas model which can be treated mathematically from start to finish, and for which we have exact representation of macroscopic limiting equation. So at least, I mean, that could serve as a kind of benchmark for a different problem. And I'll try to explain why we have this representation and therefore how it can be modified and still remain valid. Don't need to do the maths behind. I mean, so the starting point is indeed modeling reaction diffusion, and after that also modeling fluctuation, large deviation for this type of model. It's the first, let's say, basic model I'm going to explain. I know it from a paper by Demassi, Ferrari, and Lebowitz. And this model at least was introduced a long time ago, and it goes this way. So you have a particle system with some holes, particles, maybe more holes and maybe more particles, and basically at each site I, you have a variable eta I, which can take two values, not more than that, empty or full, and you play the standard symmetric simple exclusion model, where a particle can jump to the left and to the right. So you have a symmetric simple exclusion model. You have indeed, as in this, so you have random dynamics and you hop to the left or to the right. And in case you attempt to jump on somebody who's already there, you prevent the jump. So that's the first ingredient, and this is the diffusion part. And the reaction part, basically, you are going to add as well possibility of creating some particles. So you may want to add a particle at site I, and this you will do with a rate Ci, and depending on the configuration eta. So maybe you will be allowed to add somebody only if the next nearest neighbor are empty. I mean, you may have some interaction depending on other people, and you have also with a different rate. Let me call it AI eta, possibility of erasing this guy. So these are no, it can depend on a certain number of sites around you. Maybe not an infinite number, but you can really have a complicated, relatively complicated interaction. I let you imagine. And when you look at the evolution, so you have that plus annihilation. Annihilation and creation. And when you look at the evolution of what should be, let's say, at a certain point and at time t, the expectation of eta I, exactly as Bernard has explained, you will have the symmetric simple exclusion part. So this is a kind of discrete chance, theta I here, and then you have the other rates due to you may create someone at site I if it was empty before, or you may remove someone with some rate if it was full. Okay. So far I didn't do much, and as it is, I need to tune a little bit the rates, because essentially at the moment a particle may hop, let's say 3 times and then be annihilated or created. And I would like to see some diffusion, and I would like to see the reaction part. So essentially, what we want to see is some diffusive effect. So if a particle starts at some point, and let's say I want to rescale things, so I have a system of length n, and I want to see the effect of the diffusion over a certain time t. So I need to accelerate this jump rate such that a particle has some time to move macroscopically. So I want basically to, instead of having jump rate of order 1, I need to have jump rate of order n squared. So the whole system now has a length. So this is a microscopic length. And at a macroscopic level, this will be sent to the unit interval 0, 1, let's say. Okay. So I want to accelerate all the jump rates. And of course, there you'll feel much more at ease, because if I do that, here I'm going to add some n squared, it goes much faster, and you recover the a Laplacian, discrete Laplacian, and when you take 2 derivatives, you need to multiply by n squared in order to balance the thing. So what we see here is the first part of if rho is the macroscopic density. So now I've rescaled everything, I have a certain time t, and I have x, which belongs to 0, 1, and in this way we recover this derivative, this Laplacian of the symmetric simple exclusion. Just the time scale is correct. This one has been accelerated by n squared. This one, however, is not accelerated, and so it happens relatively rarely. But it's exactly what we want. If we have a particle, and if we want to see the diffusion, indeed, with this rate in a time of order 1, it's going to move by a distance of order 1, and maybe it will be during this time with, since it has a rate 1, maybe the particle will be annihilated. So there's a good competition in this way between the diffusive part and the reaction part. Yes, I could have accelerated time. It just, I prefer to do it this way. So essentially, indeed, in a particle in a time of order 1, the particle will move macroscopically of order n, and will have roughly a probability of order 1 to be, let's say, killed or annihilated. But the good point here, and that was the key of the mathematical study, in a sense, it's in terms of invariant measure or steady state, it's a disaster, because symmetric simple exclusion has some invariant measure, a product measure. But if I start to change the dynamics by adding creation and annihilation, I destroy this invariant measure, and essentially I have no idea how it should look like. But here we have decoupled the two effects. We have indeed symmetric simple exclusion, but in a huge amount. I mean, particles diffuse quite a lot before starting to be killed or to be created. And that is important because it means that locally, if I look at a relatively small scale, I will have a lot of diffusion there. And essentially, locally, my system will relax to the local equilibrium, which is given by the symmetric simple exclusion. So the symmetric simple exclusion is going to give me a locally will look like invariant. It will look like a product Bernoulli at density rho. Yes. This is just the fact that the symmetric simple exclusion moves really fast, and therefore it equilibrates according to its structure. And then, from time to time, this now is seen as a perturbation of the local equilibrium, and therefore I know exactly how to evaluate it, because what becomes relevant at point, let's say, so x now is fixed. So at some point at site I, which is equal to x times n, or here, what I'm going to do is I'm going to create, I have a creation which depends on 1 minus eta I, indeed. I have an annihilation which depends on AI eta eta I. And this is somehow, this effect is basically occurring as if I was considering the product measure. So it's the expectation is respect to the product measure at density rho x. And this is evaluated under the product measure at density rho x. So, yes. Yes, much smaller than at the microscopic scale. You will not see indeed the correction to. Sorry, no. It will be much slow. Yeah, I would say it will be 1/n. That I never really computed. What the next order, which is the fluctuating hydrodynamics, that is 1/square root of n, and still you can write it as if considering this approximation. So the next one should be indeed 1/n. In a sense, the closer you go into this refinement, the more you see. The point in this game was to decouple the two effects, but indeed, at some point, you will feel it. Here, you mean? Okay, so there is a trick, and it's a trick of the fact that the symmetric simple exclusion, what you will see is basically if imagine your particle is going to move from I to I+1, like that. So to move, you need to have one particle and 0 over there. And in a sense, there you lose somebody. And on the other hand, you have I+1, which might bring somebody to you if you're empty. And then the magic of symmetric simple exclusion is the terms eta I+1 and eta I+1 eta I, the product disappear, and you do get only a difference. And that's why things are so simple in this case. You get a difference. Doesn't mean it's even so, it looks very much as if you had independent particles. It's not, and they are in the fluctuation and so on. You will recover the interacting structure, but at this level you don't. Thank you. so let me basically this term is now, and you can really evaluate it depending on your choice of C. It's just a creation term depending only on the local density at the time, minus some annihilation term depending only on the local density at the time. So, for example, if you want to consider some fancy creation and annihilation term, you can really end up with a reaction diffusion. Let's say let me call it V prime of rho, and with V double well. V of rho, which has a double well structure, or you can really mimic as if you had a phase transition. So that's and it's very easy to tune such a V, because you just have to have a CI depending on a few neighbors. For example, you can do as if this creation and annihilation were coming from Glauber dynamics. And think, let's say, for Ising model, where you have some interaction. And the point is that it's not as complicated as, I mean, the rates are coming from the Glauber dynamics, but ultimately, you have a huge help from symmetric simple exclusion, which restore a local equilibrium under a product measure. So you can always compute these things. I have a few examples, but maybe I won't explain them. So now we can again follow, try to add a few more things in this model and follow Bernard's lecture. So Bernard said, I'm interested in boundary conditions. So you say, okay, we're going to add some creation, let's say with rate rho 1 here and rho plus 0 rho minus 0 here at the boundary, maybe here a different rate and so on. So that will simply again it will not change anything compared to the case treated by Bernard, which was let's say symmetric simple exclusion with boundaries. So you just had now you have boundary terms with this strategy, and the equation remains untouched. What can you do? You can add drift because so as not any drift to remain in this class of model, diffusion is very important. So the type of drift you can add is, for example, instead of jumping to the left with rate 1, or sorry, with rate n squared, you will jump with rate n squared times exponential minus lambda over n. So it's a tiny n. In this direction, you may jump with rate n squared exponential plus plus, let's say here, minus there. So it's a weak asymmetry. So this, for example, this model is called WASEP for weakly asymmetric simple exclusion process. So weak asymmetry. And this weak asymmetry now is going to induce some drift term, but it's weak enough so it doesn't destroy the Laplacian, the diffusive part. So here you would get terms of the form minus, there's actually a 2 lambda because the field is in both directions, dx, or 1 minus 1. So this weak asymmetry gives you a small, I mean, a drift. And you see with very elementary modeling, you can already take into account equation with diffusion part. Very important. I will never remove the diffusion part in the talk because this diffusion part is essentially controlling this one because it imposes its invariant measure, and also I can average under this part. So in a sense, if you look at the scale, you have n squared for diffusion, 1 for the creation and annihilation, and n for the drift. So in this model, everything has been quantified and acts at different level, and this decoupling of scale makes it super easy to handle. And that's the only reason why things work, and at least work easily. And now again, if you follow Bernard's talk, you know that somehow symmetric simple exclusion is a nice model, but you have a whole class of other models. You could imagine other diffusive dynamics like zero range process or other things, provided you remain in the class of gradient dynamics, okay, which Bernard talked. But for today, so basically you can make things a bit more complex and have a nonlinear diffusive term, but okay, still the class of microscopic model, to get that is okay. So now I want to, so now we have the macroscopic behavior, and in the second part, I want to discuss large deviations for this model. So again, for those who were there, Bernard explains that in this type of symmetric simple exclusion, what is relevant is, on the one hand, the density is moving according to some current. So let me call it Q dot. Right there, I'm changing the notation. That's time T and X. So that Q dot will be the local current of particles. Sorry. So just locally, I mean, the density varies because I mean, some particles are flowing here, others are coming in this box in of size dx, and so it's a derivative. I'm writing everything in 1D, but it can be done easily in a higher dimension. Just the derivative of the current flowing in the system. So in this type of model, it's not enough. So that was for symmetric simple exclusion. So in this type of model, it's not enough because let's say if I look at one particle at site I, indeed I can change U to the current, the flux of particles, but I have also some effect because some particles can be created from here or annihilated from there. So I will have to add two other sources of current, K plus dot, which is the amount of creation locally per unit time, and K minus dot is the amount of annihilation per unit time. So this gives me now something tiny bit more complicated, but not much more. K plus X minus K minus X, which most often you want to write as a new current K of X. And now once you have that, we can now relate this currents with the hydrodynamic expression over there. So as we've seen already in the case of the flux, I mean the particle flowing through the diffusive dynamics, Q dot of Tx, what is it? It's like by Fourier law, it's minus dx rho of Tx. So that gives me the Laplacian. Maybe I added there the drift, so I think I did like plus 2 lambda rho 1 minus 1. So this is for the diffusive current. And now the K plus of Tx is simply this coefficient, the creation rho Tx, and the K minus, sorry, well, let's say the total is C minus A of O. So my picture is that here.
So it's K, the thing is K dot is K dot minus K.
Oh, sorry, dot everywhere. Yes, sometimes we tend to keep K for the integrated version and K dot because it's K dot. So now once this is done, we can again we go back to Bernard's lecture and we say, okay, we want to see the large deviations. So the large deviations are now we have three guys who are or three players: the density, the fluctuation current, and the creation annihilation. So what is the probability of observing now a certain density over a certain time, T less than T, a certain profile of current, and a certain profile of this annihilation creation current. They have to be related because this law, we can imagine crazy things, but we can't imagine to break this law because by construction it's there. So this gives me some functional, which I would like to comment. So it's a functional which depends on n, on t. It scales like n in my scaling, and it depends on the whole trajectory of t, t. So it's not a big surprise to you that if I remove the creation and the annihilation, then the functional will be the one of the diffusive process. So this functional over the time interval of rho qt kt, we have two parts. One is the diffusive part. So it's the integral of time over time. One integral, let's say my space, my macroscopic scale space is now 0, 1. It can be a larger dimension, but let's make it simple. And now what is the constant? Well, this guy should be equal to this quantity plus some Gaussian fluctuation. So if I go at the hydrodynamic or the fluctuating hydrodynamic level, I have noise here. And the noise is the Gaussian noise. So there I can write it. It's Q dot plus dxo minus 2 lambda rho 1 minus rho. Nothing fancy, it's just I take this thing and put it there, that's the mean. And then you have a deviation which is proportional to 2 sigma. Sorry, sigma in my model, maybe I should have done that before, sorry. Sigma in this model, sigma rho is rho 1 minus rho. But again, I mean, what is important is exactly, I'm using the same notation as in our lectures. Sigma rho is a fluctuation. And in this case, this is also sigma rho. So this is the part. What is easy in this model is everything decoupled. I mean, the diffusion is much faster, so I have really 2 levels. And the second part is more, a priori, more complicated, but I would like to show you that it is in fact, so the second part is a function which depends on rho at point t and x, and which depends on k, point t and x. So this function is ugly, but or looks ugly. Maybe I don't know whether oh yeah, maybe I just write it, so I would have done it once. But as it is, I don't think it's particularly enlightening. K dot square plus 4 AC plus K dot log of square root K dot square plus AC plus K dot okay. So A and C are AC of rho each time, and sorry. So this, yes. So C is C of rho, A is A of rho, AC is A of rho, C of rho, and so on and so forth.
It's C minus A or C plus A.
Here it's C plus A.
But up there we have C minus.
Yes.
Yes, so it's what?
I'll tell you where it comes from, because as such, I mean, it's really ugly, and I would say it's really hard to have an idea. Yeah. Yeah, sure. And so you'll see. And it's actually of two quantum meters. That's why it looks like. And it's exactly that. So so you can see it. So and indeed, as I said before, everything in this model decouples. So when you want to understand over a short time, what is the flux? Well, so let's look in a tiny window of length L, and over a time dt, over a time, let's say, yes, of length or during the time dt. And in this case, and I'm going to look only at the creation process, K plus. So a priori, on average, K plus during the time dt, that should give me dt creation of rho x. So that should be the number of particles created during a tiny time scale, because essentially everything here is averaging according to the density of rho tx. And actually, what's happened is that I have Poisson processes at each site, and this Poisson process have L, it acts like L independent Poisson process with rate or since everything is average with rate C of 1. So the creation, there's the diffusive dynamics helps averaging out, and the number of particles creating in this way is just given by at least on average, it's just given by a sum of L independent Poisson process with rate 0. So if I have L independent Poisson process, it means that in total the probability that the creation or the number of created particles will be let's say A. This is equal to A. To the mean. So it's L times, let me call C of rho, let me call it C. L times C, A, divided by A factorial times exponential minus LC. So L is huge, and this is an average over time, so it's during the time dt. So this is really the computation we want to do. I mean, everything is averaged out, and I have the sum of the total number of created in this little part. It's exactly the joint report of L-independent Poisson process maintained thanks to the symmetric simple exclusion to the correct rate CFO. And when you do the computation, let's say if so, the A you expect that it's of order N times dt, and that could be the correct A you want, and you get indeed exponential minus L dt, and then let me call this psi of A, and psi of A is equal to A log A over C minus A plus C. Maybe small a was not such a good idea, so let me call A, maybe let me call it K plus, the number of particles created. And so now A is, I hope you, sorry. That's, so now we have the large deviation function for the creation rate. And actually what's going on is that at the same time, I have another process which gives me the annihilation rate, and particles are moving out. And the process I'm looking for is the sum of the two. So I know that thanks to this decoupling mechanism, I have I'm looking for a process K dot, which is the sum of these two, and for each of the K plus or the K minus, I have the large deviation function associated with just the Poisson process, which, I mean, this guy you compute just use scaling formula and it comes out. So it's not a big deal. And therefore, what is the large deviation associated to, let's say, large K? You want this, the probability that this guy is gamma times, I mean, properly risque, that the large deviation function, so maybe there I should write again. So L is super large and dt is what it is. Again, I will have a scaling, which is L and dt. And then I have to optimize. If I want to produce a number of gamma particles, I have to optimize the efforts of the creation and the annihilation. So I'm looking now for the best K plus and the best K minus, such that K plus minus K minus is equal to gamma. And I have the efforts, or this depends on the creation C of K plus, and this depends on the annihilation rate A of K minus. So let me summarize. The part over there, which looks actually super ugly, is just the combination of the sum of two processes, Poisson process, which themselves behave very well because of the global averaging of the symmetric simple exclusion process. So, and if I want to observe a large deviation of this combination of the two processes, I have to optimize the cost of both. Each of these costs, this one is very easy to understand, and optimize in terms of K plus K minus in order to get the right amount. So this formula is ugly, with just the optimization of these two values. And that's it. So now you can one thing you can do. So, but basically, the game is just the following. We have two terms. One term taking into account the large deviation of the diffusion. One term taking into account the large deviation of the creation and annihilation, and both are related through the conservation equation d0 equal minus dq plus k. Imagine now you would be interested in the large deviation of the density. So density large deviation. Well, what you do is, so now what's the probability of observing a certain trajectory routine? You don't put any constraint on the rest. Well, it's just this will be given by the increment, sorry, by exponential minus n, the increment of the functional of rho t q dot k dot. And what you do is you optimize over the best the joint q dot. Okay, you optimize over the joint effect of the currents now, the diffusion and the creation, in order to get something. This functional was already discovered, not going through this way actually at all, by Bodineau, Landin, and Vares in 1993. So this functional, which actually once you take the increment, it only depends on rho, and they derive this. Okay, the large deviation result is a joint work I did with Maxime Lagouge. Let me write your name. So the large deviation, which is here, is a joint work with Maxime Lagouge in 2009, so some time ago. Yeah, so I'm sorry, I'm not presenting new results, but I felt it could be of interest to review all these things. So now, if you are convinced by this simple reasoning, you see that you can essentially, provided you respect a few basic rules, which is the decoupling of the scale, you can model quite a huge number of dynamics. You just have to tune A and C and so on in order to see many things. So that's the game we played in the case of active lattice gas. And okay, so from my point of view, okay, first of all, I would like to say that I'm absolutely not expert on active lattice gas. I'm really coming from this type of parts of the statistical mechanics. And so there's a huge number of references and so on, which I won't be able to quote. But I wanted to mention this work, which we did a few years ago with, and I'm going to write the name, Courban Hussein, Clément Erignoux, and Julien Tailleur. But essentially, the idea was to say, okay, if I tune well my parameters, I can essentially, with this model, recover some phenomenology of active lattice gas, like MIPS or collective motion. So for me, I saw in 2010 or so, I saw a talk by Uchate, and I thought, oh, that's nice. We can certainly, I mean, find a few models which would do the job. And I gave to Clément and Vigneault the following PhD thesis was to say, okay, choose, now we are in 2D and you'll see for obvious reason, you choose like a symmetric simple exclusion in 2D, except that some particle will be equal plus, and we'll have a tendency to move, let's say, in this direction, and the minuses will have a tendency to move in this direction. So you take a symmetric simple exclusion, you add with two types of particles, plus, minus, you add the drift, weak asymmetry, the weak asymmetry. So we are exactly in the lambda for the, let's say, plus lambda in this direction for the pluses, minus lambda in this direction for the minuses. You can, I mean, do much more than that. And then you need you add some creation annihilation, in the sense that now the creation annihilation, when we won't remove or destroy the particle, we just change the color. But the strategy is really the same. So now instead of I mean, removing a particle, maybe you have a kind of flux, let's say, K plus, sorry, K minus, which is going to transform it. So they live on the same lattice, but let's say now my current K minus is going to transform the plus into a minus particle, a bit like before, and I have a minus flux.
I have a question. The lambda plus and lambda minus are like biasing field.
Yes, in the same form as the one I've introduced, so it's a weak asymmetry. So again,
Lambda over n.
Lambda over n, yes, that's what you. So all these things, it's much easier. So again, you have, let's say, indeed, n square as a right here. Okay, lambda n, let's say here, and right one for the change of colors. So again, once you have the scale in your system, things decouple nicely a bit as before. Minus becomes plus, and again you have the with weight, let's say K. So now it's a new current if you want, but the analogy with what I said before is exactly the same. And as a matter of fact, one thing I didn't appreciate at the beginning is this symmetric simple exclusion with two colors, if they really perform, if the particle perform really a symmetric simple exclusion and are not allowed to jump on top of each other, it's what Bernard called the non-gradient model. So, I mean, going from gradient to non-gradient is, in terms of mathematics, a huge trouble. And in terms, concrete terms, so you don't have Laplacian anymore, but you have complicated diffusion coefficient, which turn out to be quite a lot of work. But Clément et Vigneault, okay, studied this model in his PhD in a more complicated case with drifts, which are actually indexed by some angle, where the angle is now in 0 to pi. The main difficulty compared to what I said before is actually the system which was before providing all the regularity, which was symmetric simple exclusion, is no longer so easy to handle due to the non-gradient. So this is symmetric simple exclusion with exclusion between the plus and the minus. It's non-gradient, and that leads to all sorts of trouble. That's a good point. In a sense, so if they stay on the same lattice, they just change color. So the plus might become minus and so on. So the rate, essentially, you tell me what you want and you can use it. Because it's exactly as before, you can do the rate of change depending on some neighbors you see around. So you can do a rate of change just randomly without any interaction.
There's no any bias.
No, there is some bias, and in 2D you can even add a bias instead of having just one direction. You can even have a bias in some, I mean the direction you choose, and but okay, this one you mean okay. You want to rate?
What we are discussing now,
Yes.
we have any bias or any rates for
The
vertical direction. Ask what the vertical is of the diffusion and the vertical.
Let's say okay. Let's start with diffusion, and let's say only. But you see, in more general case, it doesn't really matter. You can decide that you have a. Okay, so now let me just write. You have two coordinates 0, 1. Okay, so in higher dimension, you can really put the diffusion in the direction you want. It doesn't matter. So you can put it along the lattice this way or diagonal. It's you choose. And then the only thing you want to do is possibly indeed when this is continuous, you have okay. Maybe let me remove the continuous part. And now let's say that there will be only two directions, one to the left and one to the right. And diffusion vertically. I think it's better. Thank you. So sorry for the. Okay. So time is running. So just wanted to say so. In the meantime, they were so that was okay, like around 2013 or something like that. And in the meantime, they were worked by Solon and Taglier. We were also considering lattice gas dynamics, and so we decided to combine the two works, and we came up with the following model, which somehow is much simpler, even though it looked very much like the same. But here, what was very difficult is the exclusion between the plus and the minus. But if you remove the exclusion, you can even, let's say, in one dimension, if you have the exclusion between the plus and minus, they can't cross. And yes, that's what we did, and everything is much easier. If you put it well, yes, because it becomes gradient. Because you see, there are several ways of looking at symmetric simple exclusion. and the way I explained was to say, okay, choose one particle, jump to the left or jump to the right. Alternatively, you could say, choose at a link between two sides and exchange the particle on the two sides. This is exactly the same. In particular, if you have two particles and you exchange, you see no difference. And if you have two voids and you exchange, you see no difference. And if you have one particle and another one, you exchange, well, it boils down to have this jump. So you can basically, in your system, decide to exchange particles on all the links. So you have now minuses, some pluses, some voids, maybe several pluses, some voids, some minuses, some pluses, and so on and so forth. And randomly, you choose an edge and you exchange the particles. So in particular, the plus and the minus can cross, and you do exchange with rate and square. This is the equivalent of symmetric simple exclusion. Now the drift you do with rate n, and or lambda n, and the idea is a plus can jump only if there is a void. With rate lambda n, a minus can jump on the other side only if there is a void. So it's like weak asymmetry. And you have also creation and annihilation. And the outcome is exactly the same. And so now we kind of remove all the difficulty of the exclusion between the plus and the minuses. And we have now a density of pluses moving like this. A density of minuses sorry, I'm running out of time, so I'm going to conclude very soon. And then you have a parameter. Let me call it gamma, which depends on rho plus and rho minus. This will and minus gamma. It depends on rho plus and rho minus, which are now just the outcome of the reaction terms. And depending how you tune the switch here, you have different terms, gamma, rho plus, rho minus. Actually, maybe I can even, just to have a clearer comparison with most, that really means at the end. Okay, sorry. Maybe let me say that you have a creation with like rho plus, rho minus, an annihilation with like rho plus, rho minus, and there you have, since it's a conserved quantity, you have the opposite. Okay. So depending on how you tune and so it's really over now. Let me just conclude. I want to show you one picture. So for the maths, everything is exactly as I said before. So this model, they work relatively well. You can compare them with simulation. And now you just choose the rates you like in order to produce either MIPS type of result. So maybe there you can see like you have a block which has been formed, and or collective motion. It's just whether depending what you want to do, because for example, if you want collective motion, it's enough to port the alignment through this creation and annihilation. Again, they can be computed explicitly because you just evaluate them under the product measure with density rho. So there's no, whatever type of alignment you choose, you can really get something. Then if you want MIPS, well, you take something easier here, but you have the exclusion effect. So it's enough to produce the exclusion needed to create MIPS. And if you want large deviation, you just take that. I wrote before, I erased it, and you can also compute the large deviation for the model. So I want to say that for the large deviation in the case of MIPS, this has been done by a group of people, which I want to quote before concluding, Adranov. So the large deviation for a MIPS type of things by Adranov. And I'm sure I'm omitting so much literature, so I want to apologize. Carefully. And look. But what I wanted to say is that if you have a favorite model you want to study, and you can tune, and if you want to see some particular effects, you can tune these parameters, and the large deviation will be exactly the one I wrote before. Just because the decoupling is the same, and for the same reason, one would observe the same structure. Thank you very much.
Thank you very much for the very nice and clear talk. Are there any questions, comments?
So when people define these models, do they think about something like local detail balance? So not necessarily. I mean, because in this case, it has been for example, in the case where you have reservoir and symmetric simple exclusion or something like that, you have local detail balance. There we broke it from the start because we put two dynamics or two microscopic dynamics which are incompatible. One is symmetric simple exclusion, let's say, which would be, which is compatible with product measure. And this one, creation and annihilation, which is more like a global type dynamics, to be interesting. So there you, a priori, you don't have local state balance.
Because this active lattice gas model, for example, the rates looks like the first two terms of an expansion of some Glauber rates, n squared, n squared over 1 minus e to the lambda over n.
Mm-hmm.
Yeah, so I was wondering if there was a local decoupled balance was a concern.
No, not that I know. No, I would say on the contrary. I mean, it really doesn't. A priori, at least microscopically, it really doesn't work. I think then the concern is more depending on what you want to observe. You tune your parameters, and the good point is that you have the macroscopic coefficient for free, and there's no. Indeed, there might be 1 over n correction, but at the dominant order, they correct.
Does the description of boundary conditions remain for active lattice gas equivalent to what you have for the reaction diffusion?
In the regime we consider, yes, in the sense that there we have this type of model. Okay, there might be many other ways and weak boundaries or something more fancy, but let's say in this case, what people tend to consider open is just fix the boundary by adding or putting a very strong creation annihilation at the boundaries. And in this case, it will be exactly the same.
Other questions, comments? I have one. So in the case of simple exclusion process, in the end, it's coming from the solvable models. So after obtaining this kind of equation, one can do a lot more, right? But in this kind of case, what kind of things or how much you can do with this equation?
In terms of solvable model?
No. It doesn't have this. In the case of solvable models, for example, one can study stationary situation by solving it. But in this kind of case, what kind of thing can you actually do?
That's, I guess, that's part of the problem. You see there, for example, for this, you can now, with the large deviation function, you can write the equivalent of the macroscopic fluctuation theory. You can write anything. Whether you can solve it is another thing. So the point that they're becoming super complicated. I mean, you have tons of currents, tons of parameters. So it's very hard after to get close equation. I don't have any.
We don't have to really solve, but what kind of analysis can you do with these equations? Here.
But sorry, but one of the basic things, but I think this has been done. I mean, our work, but after much more in many other works, is also to look at the stability of this equation, whether you have phase transition or not, and how it behaves. That's, I would say, the first point. But then you may ask more complicated things on the current, indeed, on the structure of the stationary states.
To study stability, one has to find something, no?
But not necessarily. I mean, at the end, at the beginning, for example, if you think of MIPS, you say, okay, I'm starting in a state where the density, the stable density is uniform rho plus and rho minus, and I would like to know, depending on these different parameters, and this one which I haven't tuned, in which region this remains stable or not, for example.
So there are some kind of trivial solution that you want against the
And around that, yes, you try to look at.
Other questions, comments?
One question, I mean, about the tuning of the parameters. So you say, I mean, what exactly does that entail? So, in order to get, what do you have to do to get things to behave nicely? Because you said you have to tune parameters. It wasn't clear to me exactly.
Okay, no, so it depends whether, let's say this in a sense, there are different tunes. Well, the main one to get this macroscopic equation was the separation of scale, and that's it.
But I'm talking about your C's and A.
Well, that
So what's the process by which
one chooses them.
Yeah.
It's I would say it really depends on what you want to model. In a sense, if you want to model something like MIPS, the easiest thing is just to have C is let's say gamma rho plus, and A is minus. Gamma rho minus, and like just independent flips, because you don't want to put too much structure in this. Then they want to tune the gamma and the lambda in order to see the formation of patterns. But in case you want collective motion, then you would say, but maybe the plus and minus, I want to put a kind of Glauber dynamics as an underlying way of tuning so that all the plus are going together and or have a tendency to accumulate. Then you have a lot of room.
That's what I'm asking. So, but you could actually imagine that if I was thinking of blocking, and I would say, I want somehow to have my rate to be biased by the neighbors.
Yes. And you see, the good point with this strategy, if I may say so, is that the CI theta is just a local function of, let's say, eta minus 1, I, eta plus 1, and as many as you want. And that this guy is just the average of this local function with respect to a product measure. So you can really try to sort the type of structure you want to see. And usually it's very complicated to have expression in the hydrodynamic, but there, very simple exclusion is there for you. And you just have to evaluate it under the product measure. So it's easy to, but now, by the way, if you want something, you say, I need more particle per side. Maybe you want to have a zero range process. Okay, the zero range process will be the dominant thing, and you don't evaluate with respect to the product measure, but to the measure of the zero range. I mean, the invariant measure of the zero range. So again, you have some room to add diffusion coefficient and to have again exact structure there. If you go outside the class of Bayesian models, or let's say there things have been done, but it's very complicated.
One more question. So can you also study something about the fluctuations?
Oh yes, it's embedded there. So the fluctuation here, you see, you will again it's decoupled. So you will have the fluctuation of the diffusion current from this, and you can write it as usual, like fluctuating hydrodynamic. I can do it, and you have the fluctuation there due to a bit like here some average of Poisson process. So the Poisson process fluctuates as of rate C fluctuate. I mean the variance is C. So
can you study what happens near the phase transition point?
But that I never studied, but and also you have to aim well to find the transition point and so on. Okay, that I don't.
That you can study the stability.
In principle, in practice, I mean, it's complicated, but yes, okay, that I haven't done. That could be interesting.
The weak long range correlation.
Again, okay, by construction, I think you would get a weak long range also, except that now it will also depend on your A and your C, so you probably have some exponential decay due to the. So let's say, I mean, if you look at the most basic one, minus, let's say, C of, or let's say minus rho or minus gamma rho. You have some exponential decay due to these guys, and so I would say you may have exponential decay if you linearize around something like that. However, already at the beginning, when you have V prime of rho and the V prime is non-convex, then you can have really huge instabilities and other things. So it's relatively rich.
No, but I mean, in this context, the fact that rho plus rho minus is concerned,
Yes.
and you have an isotropy and it's out of equilibrium. Wouldn't maybe you rho plus rho minus fluctuation, they have a one large square, etc.
Okay, I see what you mean. But well,
Generic scaling variance.
it will also depend on the phase. I mean, because if you start to create bumps, I don't know what will be, but indeed, I would say in a phase which is homogeneous, I would expect similar structure, and in this case, they will be geared by really the diffusive part again, and the other one might do some damping a little bit, but I don't. Yeah,
But I guess that basically coming from the symmetry of your C minus A.
Yes, back to
And this imposes, I mean, for application space, and the application would never make it. This for well fluctuation. I guess that's how you would recover something like
You mean this version of plus rho minus will show nothing, but all the things are cancelled.
That question more answered in the.
In your.
I mean, in the homogeneous phase, we have the with correlation length, they're very good. Once you approach it.
So you're one of the authors?
Yes.
So okay, pleased to meet you. Sorry, I had no idea. Because I did, okay, I haven't made many contributions in this work in 2018. So in the subject, so I try to gather some references, but I'm sure I omitted several. Sorry.
Any other questions, comments? If not, let's thank Thierry again.
Thank you.